Welcome to The Quantum State, a podcast exploring the latest research and innovation in quantum computing. Join us as we dive into groundbreaking breakthroughs, trends, and news shaping the quantum landscape. Discover the cutting-edge developments pushing the boundaries of computing technology. Through insightful discussions, expert interviews, and in-depth analysis, we unravel the intricate theories and real-world applications driving this transformative field. The Quantum State also offers updates from BTQ, sharing the company's research progress and innovative products at the forefront of quantum computing. So, embark on this mind-bending journey with us as we navigate the realm of quantum computing, witnessing its potential to revolutionize our world. Welcome to the Quantum State podcast. So today we have a guest, Dr. Duncan Wong from the Abelian Foundation. Abelian is a post-quantum privacy-preserving blockchain network which adopts the NIST standardized lattice-based cryptography. Thank you so much for coming on the show.
Thanks for having me.
All right, so tell us a little bit about yourself.
Sure. So I'm Duncan. I live in Hong Kong. So basically, I grew up here in Hong Kong, and I got my first degree in electrical and electronic engineering. Then after getting the master also in Hong Kong, I went to Boston, Northern University to study cryptography. So at that time, I was doing key exchange, encryption algorithms, doing that kind of research. After that, I went back to Hong Kong, being a professor for 12 years. Doing research, teaching cryptography, computer science subjects, all that. And a few years ago, I started up this project. And here I'm working on this post-quantum blockchain project Abelian. Yeah.
Great. So what motivated you to create Abelian?
Well, so as you can see, I'm basically a tech guy. I've been working on encryption, digital signature algorithms, basically all my career. So when I'm looking into the blockchain industry, what I'm seeing is that what would be the next big thing for blockchain, and we all know that for blockchain there are basically three aspects. We call it the blockchain trilemma. The scalability, the security, and decentralization. So when we talk about the security part, we always think about what would be the next big thing. As a cryptographer myself, and we have been looking into like post-quantum cryptography for many years already. Actually, more than a decade, or more than two decades. The problem over here is that when I look into those blockchain schemes, for example, like Bitcoin, Ethereum, or all those major blockchain, they are all based on so-called elliptic curve cryptography. So elliptic curve cryptography was invented back to the 80s. It's not secure against attacks from a general or mature universal quantum computer. So it's based on some of the number theory hard problems that we all know that there exists efficient algorithms which can break it if we have efficient quantum computers. So this is actually the motivation of building Abelian, is to see whether we will be able to build a public blockchain which can secure against not just the conventional computers, but also the future quantum computers. That's actually the major motivation that we started doing the research about the Abelian blockchain about 5 years ago. Yeah.
It seems the very defining feature of Abelian is the post-quantum security that it introduces compared to other blockchains. But blockchains have many, many different features beyond just what type of security they use. How does Abelian compare to other major blockchains in terms of functionality, the different types of things it's capable of doing?
So, in fact, in addition to post-quantum, we actually focus a lot on the privacy-enhancing technologies as well. So first of all, I would like to consider the quantum resistance as the foundation for Abelian or for the future blockchain systems. So this is kind of like a preliminary requirement, is that we hope that the next generation blockchain systems will all be post-quantum, will all be quantum resistant. In addition to that, for our team, because we are basically a bunch of cryptographers really love these privacy enhancing technologies, we call it multi-tier privacy preserving technology on Abelian. So what I mean is that we provide, first of all, the basic privacy enhancing technology, which is very similar to Bitcoin, Ethereum, that it's anonymous, but it's traceable. But we also provide several options to the users. For example, the users can actually use Abelian kind of like a privacy coin. They can have their addresses encrypted. They can have their transaction amount encrypted or hidden as well. So it's up to the users to choose what kind of privacy level that they want. So this is one major part that we have been focusing on, developing and doing research. And the major part is that we also hope that we will be able to support other users to issue their own post-quantum tokens. So it's kind of like the BRC20 on Bitcoin, that we would also like to support other users to issue their own tokens, even stable coins, that they are post-quantum. So these are the two major things. If we have time later on, I would also like to talk about the bridge, which is a post-quantum bridge that we make use of some lattice-based zero-knowledge proof system to build a bridge to connect Abelian with other chains as well.
Great. So maybe now's a good time to dig into that. I was just wondering, could you give a little more detail about how Abelian uses post-quantum cryptography to ensure security of the blockchain network, and what components of a blockchain network are vulnerable, and how do you make those safe?
Sure. So if we look into, let's just use Bitcoin as an example. Say if we look into the Bitcoin system, and if you think from the hacker's perspective, say I were the hacker, I got a very powerful computer, how am I going to attack Bitcoin system? So what I'm going to do is that I would just look into the ledger, and then I will be able to find all the public keys. So those public keys are elliptic curve public keys. Because I have the powerful universal quantum computer, and then I can apply the Shor's algorithm, that I can basically just compromise the private key from the public key, the elliptic curve public key. So once I, as the hacker, I got the private key, I will be able to own the wallet. So basically this kind of attack is disaster, because you can basically just reverse all the public key to their private keys, and then the attacker can basically own all the wallets on a particular blockchain system if it is quantum resistant. So this is the threat, and this kind of threat is actually getting closer and closer. And in order to defend against this kind of threat, we basically need, for example, the underlying digital signature algorithms be quantum resistant. For example, on the Abelian system, we make use of the technology which is called lattice-based cryptography, which is quite different from elliptic curve cryptography. So by making use of lattice-based cryptography, we designed the digital signature cryptographic algorithms based on this lattice-based structures. And it has been well studied for multiple decades. That lattice-based cryptography so far is against the attacks from quantum computers. Yeah.
I'm interested from a very naive theoretician's perspective here. If you want to substitute the cryptographic algorithms in the blockchain to become post-quantum the way you have, if you consider, say, lattice-based versus existing elliptic curves, at a high level, the API is effectively the same. You have a sign, a function that signs something based on a signature, a function that verifies a statement based on a signature. Why is it not the case that a blockchain can just substitute the cryptographic libraries problem solved? Why is there, where's all the work? What am I missing here?
Yeah, that's a good question. So if you think about just simply so-called upgrade the existing blockchain systems by replacing the elliptic curve cryptography to lattice-based cryptography, by theory, it's actually pretty straightforward. The most important part is really thinking about how to handle the large keys and large digital signatures. So this is actually the main challenge. If you just think about a simple upgrade of the ECC elliptic curve cryptography to lattice-based or other kinds of post-quantum cryptographic structures. So when I'm talking about the large size of digital signature schemes, as also keys, we're actually talking about, like, for elliptic curve cryptography, the keys would be just like 60 bytes long, or even smaller, 40 bytes or 32 bytes long. But for post-quantum keys, they are like 2,000 bytes long, 3,000 bytes long. So how are you going to handle this kind of large size while at the same time you can achieve the needed requirement on efficiency and the usability? Even about the signature size for a elliptic curve signature, it's like 64 bytes long, only 2 bytes long. So it's way less than 100 bytes long. But for a post-quantum digital signature, it can be 4,000 bytes long as well. So you may say, hey, let's just make the change of the data structure, put everything onto so-called the metadata part, and then we put some of the pointers onto the ledger. In fact, it's doable. In fact, some of the other chains that people are trying to upgrade the Bitcoin to post-quantum by doing that. So the main challenge that we have been doing in the last few years is that how we will be able to, as I said, build the foundation of a blockchain which is already post-quantum, but we are also offering tools to the community so that they can build things on top of this post-quantum system. So as Peter mentioned, you are talking about like just upgrading it. I also think that it's quite straightforward. But upgrading it, how you are going to like achieve different levels of privacy preserving, like how to do fully private transfer of your tokens, and how to do bridge of your system with other blockchains so that you can upgrade other blockchain to post-quantum. This is actually the part that we actually spend a lot of time to build the lattice-based zero-knowledge proof systems so that in the future, and even right now, developers will be able to make use of our tools to build some very interesting applications on top of it.
You mentioned a few of the central methodologies that you use in your blockchain, the wallet address hiding and the transaction hiding. Can you tell us a bit about how they work from an implementation side of things?
Mm-hmm. Yep. So first of all, let me talk about the feature, and then I will talk about how we make it. So about the feature side, first of all, if you think about a fully private token, for example, like the existing like Zero Cash or Monero, what they are doing, what they can achieve is that they can basically hide the sender's address and also the receiver address on a one single transaction. And also they can basically so-called encrypt the transaction volume. But the main challenge about encrypting the transaction volume is that if transaction volume is encrypted, how are you going to detect double spending, right? So for example, every single transaction has the volume, has the transaction amount encrypted. Then as a miner, as a public miner, how are you going to make sure that the sender is not overspending or double spending? So the technology of doing that is basically a combination of zero knowledge proof and commitment schemes in cryptography that we can hide the transaction volume by using a commitment scheme, so-called. A commitment scheme is basically hiding that volume, but at the same time, you can convince the public that the number has some feature. For example, you are not overspending, and then you make use of zero knowledge proof to show that you are not overspending or double spending. So what we do is that we basically borrow ideas from the ZK SNAR, which is the zero knowledge proof from the Zcash, and also we borrow the idea from Monero. They call it the ring signature. Actually, back in 2004, I was a co-inventor of the ring signature, but at that time it's a pre-blockchain thing. So we built the lattice-based ring signature scheme to protect the sender's address. So the idea is actually very simple. When you're the sender and you want to send some tokens out, you create a ring signature. A ring signature has a feature that when you generate the signature, you are not generating the signature by yourself, but you also pull in other people's public key. So you basically set up a ring or a group of all the potential public keys, so that when the public is verifying your signature, the public will not be able to tell exactly who's the sender. But actually, the public can only tell one of the public keys within that group is the real sender. So when you have this signature hop for multiple rounds, then you actually can protect the sender's wallet address by reducing the chance of guessing correctly who's the actual sender. So this kind of ring signature has been used quite certainly, quite heavily in the blockchain community for protecting the privacy. So in Abelian, we are also using ring signature, but we designed our own lattice-based ring signature in order to make sure it's quantum resistant. And also we use of the zero knowledge proof and concealment scheme to make sure the sender's wallet address is also hidden, as well as the section volume is also hidden. But at the same time, making sure that the double spending is not possible. Yeah.
Yeah, so maybe we can take a step back, and lattice-based cryptography has been studied for a pretty long time, so we feel generally secure about it. But can you explain a little bit why lattice-based is secure against quantum computers?
Yeah, sure. So if you look into, say, the existing elliptic curve cryptography, which is not secure against quantum computer, is because of an algorithm which was invented back to 1994. We call it the Shor's algorithm. So in order to design something which is secure against quantum computer, we need to design something which is based on a hard problem, a mathematically hard problem, that there is no known efficient algorithm or so-called quantum algorithm which can solve that hard problem. So for example, like for elliptic curve, the underlying hard problem is called elliptic curve discrete log problem. But turns out it's not a hard problem against the quantum computer. So for lattice-based cryptography, it's also based on some hard problems that we what we are trying to do is to introduce so-called noise into the digital signature algorithm, or the so-called encryption algorithm. So if you have the private key, you can remove the noise in your encryption, or you can basically generate the signature if you have the private key. If you don't have the private key, you will not be able to remove the noise, and which make you being unable to decrypt or being able to forge a signature. And so far, there is no efficient quantum algorithm which can eliminate noise if you don't have the private key. So basically, it's basically like a race against time. And we are trying to find some hard problems that it's not being able to be cracked efficiently by a computer. And we have been studied for decades that nobody will be able to find an efficient solution to crack it. So basically, lattice-based cryptography is about that. We will be able to find this kind of hard problem, which is by introducing noise. And this kind of noise can be removed efficiently if you know the private key. If you don't have the private key, there's no efficient way to remove the noise. And that's how we do the lattice-based encryption and digital signature.
So Sorry, go ahead, Gavin.
Oh yeah, just a question about, so people working on anything with applications to finance, and particularly things like cryptocurrencies, are very paranoid. And if we don't have any evidence that quantum computers can attack lattice-based post-quantum cryptography, but what about the issue of side channel attacks? So, for example, it was shown that the Bliss lattice-based digital signatures were vulnerable to side channel attacks from just faulty implementation on the classical side. Does your team have sort of an approach to mitigate that kind of risk?
Yeah, so side channel attack is actually a very tricky one. So if we just make use of some existing so-called reference code to implement lattice-based cryptography, it's not secure against side channel attack. For example, timing attack. For example, like in the past, people implemented the elliptic curve cryptography, but it's vulnerable to timing attack. So the timing attack is about like measuring time required to do the decryption. And based on the time, you will be able to find the entropy of the private key. The longer it takes to do the decryption, the more ones in your private key. And that kind of timing information can significantly reduce the level of hacking a system. And in fact, for lattice-based cryptography, it's not, you cannot avoid a special design in order to defend against side channel attack. So side channel attack can still be effective if your implementation is not secure enough. So you are definitely right, Gavin. We actually spent a lot of time back to 2021 and 22 to design to basically implement, not the design part, but basically implement our algorithm, which can be secure against timing attack, differential analysis, that kind of side channel attack. So this is a continuing research. It's not so-called provable security. It's different from the algorithm perspective that we can define a security model and we will be able to prove that if somebody can break our algorithm, then the hacker can basically compromise a underlying mathematical assumption. In fact, we have been doing a lot of research to make sure that our implementation is secure against kind of side channel attacks. And we are gradually publishing our source code to encourage everybody to look into it, that crypto engineers to look into that. And also, hopefully, it's a community effort to make sure that we are absolutely secure against side channel attacks. And once there's any new side channel attacks coming out, we will be able to look into that and to investigate whether our code is secure against side channel attack.
Going from side channel attacks back to just ordinary attacks directly against the algorithm, you were saying that basically we haven't found any vulnerabilities of lattice-based crypto to quantum computers yet. Now, we would have said the same thing just before Shor invented his algorithm in relation to integer factorization. How confident are we that these new cryptographic techniques are genuinely robust against quantum computing versus we just haven't found it yet? How do we, well, what's the intuition at least that guides us to thinking that it's post-quantum?
So my answer, this is actually kind of like a debatable question. Everybody, including all the cryptographers, are talking about for decades. My answer to this sensitive question is that it's all about how long that the research community or the academia and also the cryptographers has been looking or studying about the lattice-based cryptography. It's actually the same as the elliptic curve cryptography. That if we dated back, if we track the history of the research of the elliptic curve cryptography, it's been like 5 decades, right? Like half century long of study, and even longer. And until like 1994, Shor's algorithm was out. And even recently, like in the last few weeks, there was a new paper coming out as a new proof on top of Shor's algorithm, which can actually make the hacking of the elliptic curve even more efficient. So it's all about time. It's all about how many decades that you are spending, or the entire academia or the cryptographers are spending time to investigate, to analyze a particular algorithm or a particular field. So speaking of lattice-based cryptography, this one we have been studied for at least 3 decades, to my knowledge, or even longer. So in fact, back to the time when I was still a PhD student, I was already looking into those papers, and it's a little bit, it's already, I'm old, so it's more than 20 years ago that I first get in touch of the lattice-based cryptography. So it's been studied for so long, and there are hundreds or thousands of papers related to lattice-based cryptography that if we do the academic search of the papers. So it's this is one aspect. So it's all about time. The second aspect is about when that technology is mature to do standardization. Standardization is a long process. And unless the system is really mature or an algorithm is really mature, the standardization bodies will not consider of doing the standard and try to convince everybody to use it. So for example, like the American National Institute of Standards and Technology, NIST, they have been working on lattice-based cryptography standardization or post-quantum standardization for several years, back to like since 2016, that they first announced that they started the effort of doing the standardization of the post-quantum cryptography. Until recently, back to 2022, they shortlisted 3 post-quantum algorithms as the future digital signature algorithms, which they believe is secure against quantum computers. So the standardization process is a very diligent one. It's a very delicate one that a lot of cryptographers, they actually put in a lot of efforts to study, make sure this is really secure. So I have high confidence on the lattice-based cryptography because of the decades of research and also the maturity of it towards the standardization. Yeah.
That's a really interesting point, because lattice-based has been around, but one of the things we've always been talking about is the fact that for a long time, quantum computing has been just in the lab, right? It's been a bunch of physicists, and maybe cryptography has been a bunch of computer scientists and mathematicians, and there's a rare, only now in industry are we seeing kind of the combination come together. So when you say it's been studied for decades, has it been studied for decades also from the quantum physics and algorithm side, or has it been studied mostly from the cryptographer side?
So about the quantum computer part, Gavin is definitely the expert over here. So I'm not going to brag about the quantum computer side. But for the post-quantum part, it has been studied for decades under the assumption that once the quantum computer become really mature, because even nowadays, we only managed to build a universal quantum computer which has a little bit more than 1,000 qubits. And we are fighting against the noise that we need to handle in order to add more qubits there. So back to 3 decades ago, when I was still studying about the post-quantum cryptography, we were basically making an assumption that, say, there exists a quantum computer which already has like 500,000 qubits. And if I attack a system of like 500,000 qubit universal quantum computer, how they are going to do about hacking the existing elliptic curve cryptography. And until nowadays, this is getting closer and closer. And because upgrading an encryption system to post-quantum takes years, or sometimes it's actually more than a decade, to do the upgrade. So that's why the standardization has to be published well in advance. And actually, early next year, the first standard will be out by US NIST. And the draft standard was already out. And this basically symbolizes that starting from next year, the federal government, that what we are going to see, and a lot of major corporates, they are going to upgrade their systems to post-quantum.
So you mentioned a little bit about being open source, and obviously in the crypto community, there's a lot of not questions about that, but basically nobody will ever trust a closed source encryption algorithm, right? So you mentioned you're converting over to open source. Can you talk about the benefits of that, and also how your developer community is playing into that? Because you guys are doing a lot of stuff with the broader community.
Mm-hmm. Yeah. So we basically think about the open source initiative into two steps or two stages. The first stage that we have already completed is about publishing all the algorithms and also our security analysis. So we publish all the papers already on major academic conferences, which basically elaborate how we designed a Abelian system and why we think it's secure by defining all the security models and also providing the security proofs to show that our algorithms security can be so-called reduced to underlying well-known hard problems. So that stage that we have already completed. And now we are at the stage of publishing our implementation bit by bit. Actually, starting from today, we are already publishing our algorithms. What we are doing is that we are doing the security audit. We are doing some so-called refactoring, improving the documentation and all that in order to make sure the community will be able to understand and also to be able to follow up and look into some particular routines or modules and see how the community can help us improve the entire system. And also, having said about the side channel attack, this is actually a very important issue that we are also publishing our source code and also the explanation about why we designed that way, so that we can secure against, for example, like timing attack that we recently did a little patch, like 3 months ago, we did a little patch to focus on this kind of security issues as well. So down the road in the coming 6 months, we are basically doing the open source of all our code bit by bit, starting from our wallet part, and then the full node, and also the mining algorithms, and all that, and some other preliminary auxiliary codes as well. Yeah.
Could you share some examples then of how your Abelian blockchain, not just the blockchain, but also the technology, how is it being deployed by the developer community? You make these different modules of software tools available for implementation in different open source projects. Is there a lot of uptake? Is it being used for other things beyond the Abelian network?
Yeah, sure. So basically, we have the Abelian Foundation. So the Abelian Foundation is focusing on building the foundation only, so-called the nodes, the full nodes, and also the mining algorithms. And then we are actually right now relying on the community to build models, the block explorer, and also the mining pools and all that. So in fact, our block explorer was built by our partner that we got the connection in our community, that they built a very nice explorer. And right now they are also introducing some of the analytical tools to analyze the privacy, also the mining status of the chain itself. So this is basically one of the groups in the community that we are partnering with. We are also partnering with several other groups in the community that they are building the mobile wallet for Abelian. And also another team is actually integrating the Abelian with some well-known wallets, including MetaMask as well. So what we are doing right now is that we are trying to make the documentation as good as possible, as readable and comprehensive as possible, in order to support the community to build their so-called future quantum-resistant applications and issue their own tokens or issue their own tokens on Abelian as well.
So how can developers get involved with Abelian and contribute to its growth?
Yeah, so about Abelian right now, if you are interested in Abelian, you can just visit our website, abelian.info, info. So on the abelian.info, there is a documentation page that we publish all the SDK information, the API information there. Also, we have the downloads page that you can download all the software there, including like the mining software, GPU mining software, wallets that our partner built, the Block Explorer link, everything is there. We also have the Discord channel. People are discussing about the development and also the mining on our Discord channel. All those links are available on our website. So basically, for interested developers, you just need to visit abelian.info, and you can find all the resources and all the links from there.
Great.
Well, what are some of the forward plans for using this? Some other blockchains do all sorts of very sophisticated smart contracts. The interoperability with other chains that use different types of technology. What's the whole outlook for integrating this into the whole blockchain ecosystem rather than being just a technology on its own?
Yeah. So at this moment, Abelian is a layer 1 blockchain which does not have the smart contract. It's basically a POW, GPU-based layer 1 mining layer 1 blockchain. In May, we published a yellow paper about how to construct a post-quantum zero-knowledge bridge to connect Abelian layer 1 with other chains. The purpose of doing that is to support post-quantum smart contract development. So down the road, we actually have two major projects that we are currently working on. The first one is to build our layer 2, also called Sidechain, that we will be able to support the smart contract and also much efficient transactions. Currently, Abelian supports about only 30 transactions per second. Once we have this layer 2 or sidechain established, then we will be able to support at least 500 transactions per second on the layer 2 or sidechain. In order to build that layer 2 or sidechain, we need the bridge between the layer 1 Abelian and this sidechain. So this bridge is the post-quantum zero-knowledge bridge that I was talking about, that we already published the paper back to May. And the paper can also be found on our website. So that paper basically describes how to connect Abelian to any kinds of chains and make the chain post-quantum as well. So this is basically the major thing that we are working on. On project 1, we are building this bridge. On project 2, we are building this sidechain in order to improve the efficiency. The ultimate goal, hopefully by the end of next year, we will be able to connect multiple chains together with Abelian in order to embrace the entire blockchain community and contribute into the upgrade of the entire blockchain community to post-quantum.
So when you're focusing on these side chains and other projects, are you focusing on developers right now mostly, or are you working with corporations to get them post-quantum? Where are you looking at the first applications and early adopters?
So basically, we are looking into the developer community right now. Putting aside the miner community, we definitely are working out the miner community. We got huge support from the miner community. Like in the last few months, we are seeing a huge growth of the difficulty level of the Abelian system as more and more miners are actually joining Abelian to do the GPU mining, because as long as you have one GPU card, you can already contribute and start earn the Abelian token called Abels. So this is the current part that we are working on. The developer community is the main focus right now, as we are opening up our source code, and also we already have the SDK and also APIs published. We are also seeing more and more developers all over the world are looking into this post-quantum technologies and trying to build not just tools for Abelian, but also trying to make use of tools that we are offering to build something exciting on Abelian. So for example, like we have this lattice-based knowledge proof system. We have the SDK. So if you will be able to, say, build something which is related to privacy, say you want to set up a so-called virtual network on Abelian, that you want to make use of this privacy enhancing technology to make sure all your transactions can only be seen within a subset of users, you can do it by using our tools. So those tools are readily available, and all those tools are quantum resistant. So that's why we are focusing on the developer community, trying to do more marketing, trying to do more tutorial to share this kind of information with the community, and hopefully we can get more developers to be able to enjoy this kind of new set of tools. Yeah.
You mentioned just before about the increasing difficulty of mining in your network, which is a fairly ubiquitous issue in proof of work. For context, how big is your mining pool compared to some of the major proof of work based blockchains?
Mm-hmm. I think at this moment, the mining effort is still at the small side. What I mean is that, for example, like the Abelian, this network has been live for about a year, a little bit more than a year. It's still at infancy stage. I call it the infancy stage because we are still at the first era, so-called. We haven't done any halving yet. So the first halving will take place by the mid of 2025. We just passed the first midpoint, the midpoint of the first era. So it's still at a very, very early stage. And that's why we are seeing more and more miners are joining in at this early stage to do the mining. We don't have a rough estimation about how many GPU cards, but in the thousands right now, I believe, if it is not over 10,000 GPU cards already. But compared with, for example, like other kind of GPU-based mining, this number is still pretty small. But the part that we focus a lot is on the decentralization. So we actually have a lot of so-called individual miners all over the world, like in North America, in Europe, as well as in Asia. There are a lot of miners that they only have like 10 to 20 GPU cards, and they participated in the mining of Abelian at this moment. We do see some of the major farms with thousands of GPU cards trying out Abelian right now. So at this moment, I think it's still at the early stage, but very, very soon, I think the institutional mining farms will get in. And hopefully this is the case because more miners joining in, the more secure Abelian system is.
Yeah, I noticed on your website you had the set up a node in 10 minutes documentation, which is great to get people in to the system. Yeah,
exactly. And also we have a very short video, like 3-minute video, to teach everybody how to do the GPU mining as well as CPU, despite the CPU mining is almost irrelevant right now. Like, but the GPU mining is the key that we are promoting.
It's hard to get GPUs these days, though.
That's right. Yeah. Sorry, what I want to say is that you can use some old GPU cards as long as your GPU cards has more than 6 GB of VRAM. you can already jump into this mining campaign of Abelian.
Great. So for folks listening, go check it out. Try and set up a node and comment down below if you're watching on YouTube. If you're having any problems, we'll pass it on to Duncan as well. So thanks for coming on. This was a really great conversation. Thanks for explaining all the side on the blockchain and how people can get involved. So where can folks get updates on Abelian, the news and developments, and even the grant program? I noticed you have that as well. So if people want to apply, they can also apply for a grant, I see, to develop for the system.
Yeah, so our site is abelian.info, info. So abelian.info, you can find all the Telegram group, Discord channels, and all that. So our grant program, the airdrop campaign, everything will be announced on our Discord as well as our Telegram. We also have the Twitter channel over there. So all the links can be found on our official website, abelian.info. Yeah.
Great. Well, thank you so much, Duncan, for your time. And thank you for listening to this episode of The Quantum State. And thank you, Gavin and Peter, for co-hosting with me. So make sure to subscribe, like this if you're on YouTube, and find these podcasts wherever you can get podcasts, and stay tuned for the next episodes. Thank you so much.
Thanks, Duncan.
Thanks, everyone. Thank you. Thanks for having me.